Hi, my name is Jerjen. I'm an astrophysicist at the Research School of Astronomy and Astrophysics, which is part of the Australian National University. In my profession, people often ask me the question, what do astronomers do and what is it all good for? I would like to argue that astronomy has the single largest impact on the development of science, human society and culture over the last 10,000 years. Let me give you some examples. In the 9th to the 10th dynasty, about 2000 BC, in the ancient Egyptian culture, they started to use constellations of stars to keep track of time. They subdivided the stars which would rise consecutively over the horizon in 36 distinct groups which they called Baku or decans. I show you here on the right side, on the left side here, I show you Bakus which are drawn on the ceiling of the burial chamber of Seti I. Over time, 12 of these Bakus could be observed rising during a short summer night, and this concept of using stars as a natural clock led to the division of a day into 24 intervals or hours over the time. The most important event in the Egyptian year was the first brief appearance of the bright star Sirius in the eastern sky just before the sun rises. Coincidentally, this heliacalic rising of Sirius at the end of June heralded the annual flooding of the river Nile. The Nile is the only significant source of water and in this desert region, and the flooding meant for the culture and the civilization there water and fertile soil for cultivating crop. Were it not for the Nile, ancient Egyptian civilization could not have been developed. Let me show you briefly how this heliacal rising of Sirius appears in the night sky. What I show you here in this movie is you're looking to the east and we see just before the sun rises how Sirius here on the right side will briefly appear. We have the sun rising here on the left, just coming up now, and Sirius just over here is briefly visible before it gets overpowered the light from Sirius by the bright sun. In other cultures, like the Mayans civilization in Mesoamerica, they built large monuments that related to the solar calendar. For instance, like this temple of Kukulkan. This huge step pyramid had 4 staircases, and with each 91 steps going up to the top. Now 4 times 91 gives you 364, plus the top 365. So this reflected, the different steps reflected every day throughout a solar year. Priests could use this building to predict the rain cycle for planting crops, like using the natural sky and the appearance of Sirius used by the Egyptians. So they could predict the weather and make weather forecasts and could tell the farmers when to plant the crop, the corn that was the only cereal they used to domesticate. Measuring the angular separations between objects in the sky required basic instruments like a compass and ruler. And they were combined together with the mathematical concept of trigonometry to track the motions of the stars and the planets. The trigonometry concept was introduced by the Sumerian and Babylonian and Nubian astronomers 5,000 to 7,000 years ago. The mathematical method was then fully developed by the Greek astronomer Hipparchus around 150 BC. We all know trigonometry from school, and we are aware today that they are actually used in many fields in science and physics and chemistry. For instance, navigation, architecture, engineering, acoustics, computer graphics, computer games, for instance, or medical imaging. So another very important contribution of astronomers to science and human society. One of the fundamental quests astronomy is one of the fundamental quests in astronomy is actually to find an accurate model of the universe. How does the universe work from a physical point of view? The geometrical model proposed by the Greek philosopher Aristotle in 350 BC and mathematically refined by Ptolemy in his Almagest book 150 AD was accepted for almost 2000 years to be the best description of the universe. This is shown here in this drawing. What it essentially has, as the name suggests, the geocentric model has the Earth in the center, and other objects like the planets, like the moon, like the sun, are actually orbiting around the center of around the Earth. A serious competition to this model came up with the introduction of the heliocentric model proposed by Copernicus in his famous book De Revolutionibus Orbium Coelestium in 1543. This model here, which is shown here on the right, in contrast to the geocentric model, had the sun in the center, and the planets are orbiting around the sun, and the moon is orbiting around the Earth. The reason for introducing this model was primarily because the model offered a very good description of the motion of the planets, and most importantly, it was much less complicated than the geocentric model. However, that was just a separate possible solution for describing the universe. There were no observations that could help at that time, that could help to discriminate between these two models. It took another 47 years to settle the case. It was Galileo Galilei in 1610 who made use of the first time of a telescope, which is shown up here, to accurately to follow the motions of the planets and to make extra observations. That was the first time that actually there was an instrument used to observe the night sky. And it had immediate impact on our understanding how the universe works. For instance, Galileo found the 4 largest moons of Jupiter. As a consequence, he realized not all the heavenly bodies are actually circling around the Earth. This is a drawing from his logbook, and it shows Jupiter here as this star-like object, and then 4 little dots going around, and as a function of time, over a couple of months, he realized that all these little dots, which are the 4 Galilean moons nowadays, are actually moving around, back and forth. Sometimes you have 3 on one side and 1 on the other, or you have 4 on one side. So this showed that these moons are not orbiting around Earth, like predicted in the geocentric model, but they're actually orbiting around Jupiter. What he also observed was the spots on the sun. He immediately realized here that the divine object is not as perfect as it looked initially. And using the sunspots that going across the sun surface as because of the rotation, he realized, okay, this body is actually rotating. It's not stationary in space. A third important observation was the different phases of Venus. And they were not conform, that's shown here, they were not conform with the geocentric world model, which gave another prediction how the Venus phases would look like. So all these observations, with the help of one single instrument, helped to improve our understanding which is actually the right cosmological model. It was actually the heliocentric model. We know that Galileo was forced by the Inquisition to abjure, to curse and detest what he saw, but what was the important key here is that he had the tools and he can offer the tools to everybody to actually test his claim by simply verifying it looking through the telescopes. Now, one central object that plays a very important role for us humans is of course our sun. And as you will know, our sun is actually a star. The only reason why we see this star so close and as a huge bright disk during the day is simply because it's very, very close, whereas all the other stars are much further away and appear in the night sky as little dots, bright dots. Now, astronomers had to think about very carefully what is actually the sun made out of. What is it? And it took almost until the earliest 20th century to find the right answer. When you look at the movie, like here provided by the SOHO satellite, you can already guess what the sun is made out of, thanks to these very high resolution images. You can see, first of all, it's rotating and you have prominent explosions on the surface of the sun, which tells us here immediately that it looks like the sun is made out of gas. And these stars, like our sun, are gigantic power stations, which radiates all the energy out, and that's why we have here on Earth light and warm temperatures. When you look at the sun, like this image here, showing again an image from the SOHO satellite, the reason why this sun looks like as it does in a spherical, beautiful gas cloud is there is a balance between the gravitational force that pushes the mass of the sun inwards and the high pressure from the gas, the radiation pressure from the gas that pushes outwards. So a star, like our sun, is essentially just a balanced gas cloud between the gravitational force and the pressure from the hot gas. Now, what is happening in this very, very special environment? In fact, the whole star, our sun, is made out of primarily two elements. About 71% is hydrogen and 27% is helium. And in huge quantities. 2,000 million tons of these two elements make up the entire star. Because of this high mass, this large mass, and high pressures that is produced in the center, we have a central temperature of the order of 15.7 million degrees. And every second in the sun, about 700 million tons of the hydrogen gas is converted to 695 million tons of helium and about 5,000 tons of energy. That corresponds to an energy output of about 4 times 10 to the 26 watts, or equivalent of about 2 billion power stations on Earth. It's a huge amount of energy that gets produced every second out of our sun. Now, in this process of converting hydrogen into helium, there are other steps, and in this many steps, different elements, chemical elements, are synthesized by these nuclear reactions. For instance, carbon, nitrogen, oxygen, magnesium, and silicium. All these different elements are synthesized over the course of the lifetime of the star. Now, this is a very interesting concept, and it might be useful to produce energy here on Earth. And this is actually a real concept at the moment that is explored by an international consortium of different countries like China, Europe, India, Japan, Korea, Russia, and the US. And it's called the International Thermonuclear Experimental Reactor, or ITER. It's essentially a man-made sun, a fusion reactor where we exactly try to mimic these very hot, very dense environments and generate the energy in a way the sun does it at the moment. ITER is an experimental reactor, as the name says. I show you here on the left a model, a sketch. Here you have this the primary building here, and inside in the building you have a torus. This is to scale a human. In that torus, because of these high temperatures that you have, you want to keep the plasma, this very hot gas, away from any material. And to do that, you generate a large magnetic field and this is what you see here. All these different tiles are metal tiles that can help, that produces the magnetic field. So once it's operational, you have a plasma ring, a ring of plasma that rotates around this in this torus and gets heated up to these very high temperatures. And the hope is that with this experimental reactor, we can put in about 50 million watts of energy, and we get about a factor of 10 more out of it. It's about 500 megawatts as the output. If the whole technique, once the whole technique is established, there is already a next generation of experimental reactor in planning, the so-called demo reactor, where the physicists put in about 80 million watts and hope to get out about 2 billion watts, 2,000 million watts. And if that all goes according to expectations and the success is there, we know how the physicists know how to produce this energy in a safe way, then the proton should be about the time of around 2050. This new reactor should be the first commercial nuclear fusion reactor power plant that we have in the world. So in other words, we learned from the sun how the sun produces its energy, and we're using this technique today on Earth to try to generate the same way energy as the sun does. So thanks to the astronomers and physicists and mathematicians who established these processes, understood the processes that happened in the sun, we are now able to reproduce that in fusion power stations. Now you're probably wondering, the star, our sun, is made out of hydrogen and helium, and it fuses these elements into higher elements, and there must be most likely an end, because once it's all the fuel is used up, and there will be no more left. And immediately what would happen is this radiation pressure that pushes it outwards is no longer there, so the gravitational force will take over, and it will lead to the end of the star. So somehow there must be a life cycle to our sun and to the stars. And astronomers are not in a situation they actually can observe the life cycle of stars directly, but they can take photos of different steps, different epochs of the life cycle to understand what is going on, how stars form and how they evolve and how they die at the end. So it's similar like taking photos of a crowd of people and then having children, teenagers and other age is covered by this photo, and then you can make a sequence together and try to understand the life cycle of humans. So astronomers, for that purpose, use, for instance, the Hubble Space Telescope. We're looking into the region where most of the stars are in the sky, which is this white strip in the sky from the Milky Way, the band of the Milky Way. Let's zoom in and have a look what we can find in the Milky Way. For instance, this here. This is a huge gas cloud. We know already, hydrogen and helium is actually are two types of gas. So that could be the region where actually stars are formed. And indeed, it's the case. We see here actually the cocoon where stars are formed. Similar to humans, astronomers cannot directly see what's going on in the optical here, but we have to wait for a while to see what comes out of this. About 100 million years it requires for astronomers to see how the very young bright stars right in the middle of these cocoons of gas are able to, with their radiation, are able to remove the gas and make themselves visible. So the radiation pushes out the leftover gas, and we see right in the middle of these cocoons very young bright stars. The stellar winds from these stars remove the leftover gas. Now, this 100 million years, we are as astronomers dealing with very large numbers, and that's sometimes a bit confusing, but the good news is here that we have quite a good analogy to humans. Human life evolves just a factor of about 100 million slower than, sorry, human life evolves just a factor of 100 million faster than the life of a star. So we simply can cancel 8 of the digits here to have a comparison with a human, which is shown here, a baby, on the lower right side. So let's see what happens with a star, a young star group, as you can see here, what is happening over the time. After about 400 million years, most of the gas is removed, as you can see here in this beautiful constellation of the Pleiades, and we see the very blue, very, very young, bright stars that are shining with their light. So that's again comparable to humans by simply cancelling the 8 digits and get an age of 4. So very young stars that we see here in the Pleiades. Now, the good news is that the life of stars is relatively boring. The good news is for us, because our sun is so calm, our star is so calm for billions of years, and that gives us an opportunity for prosperous times for planets to form and to life develop. Our sun, for instance, is currently about 4.5 billion years old. So right in the middle, right in a middle-aged type of star that we are having, where we're orbiting around with our Earth. You might ask the question, how long does it take for our sun until it's the end, until it consumed up all its energy? And the answer is about 9 billion years. With stars, the final stages, the final phase of their life is very, very prominent, as I show you here on this figure. What I show you here is a field of stars, a gas cloud where young new stars are formed at the moment, but the arrow here indicates a very unsuspicious star that turned from 1 second to the other, essentially, died from 1 second to the other, and turned into very, very bright object, as we can see it right here. Now, astronomers, because of this phenomena, thought initially that there is nothing there, but then suddenly a new bright star is up in the sky. And they call these events novae or supernovae, for a new type of stars that they could observe. In fact, it was realized by the astrophysicists later that this was actually the end of a life cycle of a star, that this is the end of that particular star. Because all its energy was used up, all its fusion of elements into new elements stopped, and the radiation decreased, the whole system collapsed. Now you're wondering, what's going on after that explosion? We have 2 components essentially. One component is the central component right here that is a leftover from this explosion. Depending on the mass of this leftover, we get 3 different possibilities it will develop in. If the star has a mass less than about 1 or 2 solar masses, then it will turn into a white dwarf. So in other words, because our sun has 1 solar mass, our sun will turn into a white dwarf at the end of its lifetime in about 9 billion years. The stars that have slightly larger central components, about of the order of 3 solar masses, they will turn into neutron stars. And if you are even bigger as a star, you can then turn into a black hole. So it all depends essentially on how much is left in the central part after the explosion. Then there is this other component, the gas component. A large fraction of the mass of the star gets actually ejected into the interstellar medium, and we see then this as a gas cloud sitting around the central component. And that has a very important consequence for us. In fact, it's the reason why we are here today. The good news is all these chemical elements that were synthesized for billions of years in that star are actually expelled from this dying star and will form new generations of stars and planets. And that is why we are really here on Earth, because the elements that were cooked in a star are also the elements we humans are made out of. 99% of the human body is made up of only 6 elements: oxygen, carbon, hydrogen, nitrogen, calcium and phosphorus. So thanks to the fact that all these elements were cooked once in a star and were expelled into interstellar space and were reused later on to form a planet, thanks to this fact we are here today. So that concludes the first part of my talk, and I will continue later on talking about galaxies and dark matter. Welcome back to the second part of this lecture. My name is Jerjen. I'm an astrophysicist at the Research School of Astronomy and Astrophysics, which is part of the Australian National University. Now, we just learned before that there are the life cycle of stars, how it works, and when you look at the Milky Way, as you see here on the right, there are many stars in the Milky Way region, and you are probably asking the questions. I mean, if every star is a sun, if our sun is a star, you would ask the question: are there other planets out there and maybe possible life forms? This was a very important question that astronomers tried to solve. However, these planets around other stars are very hard to find because they are overpowered in their light by the light from the host star. So it took a long time to detect alien worlds. It actually took until 1995 two Swiss astronomers from the Geneva Observatory, where they could announce finally the discovery of the first planet orbiting around a different star, different from our sun. That led to this new concept, because using spectrographs led into a new research area for astrophysics to search for these exosolar planets. And in the meantime, over 500 planets have been identified as of July 2011 this year. Let me quickly show you how astronomers can detect this very faint signal from planets around other stars. I show you this here with the help of this little movie here. What we have is we have the Earth here on the left, and this very bright star that has a planet orbiting around it. In this frame here, the star orbits around the planet. It is invisible because of this very bright light from that star. However, what we can do is we can measure the gravitational effect of this planet on the star. And that is shown here with the help of this spectrum. That's a spectrum of the star, and you have some absorption lines. And these absorption lines are moving back and forth. When the planet orbits around the sun orbits around the planet, then you see how the spectral lines changes as a function of time. So over time we see them moving back and forth. Sometimes the star is coming towards us, and sometimes the star is going away from us. And that is shown in the fingerprint in the spectrum. So that's an indirect way of identifying planets around other stars. Let's come back to the question, how big is the universe? We learned about the geocentric and the heliocentric model just in the first part of this lecture, and let's go now into the 20th century and see how astronomers learned more about the size of the universe. As part of this research, the fundamental question was there: how far are objects like these spiral nebula that I show you here, a couple of photos on the left and here on the right, how far are these objects away from the Milky Way? Now this is the Milky Way with all the stars, and when you look with the Hubble Space Telescope or with other telescopes into the different regions, you identify these spiral nebula. And the fundamental question was, how far are they away? Are they part of our Milky Way or are they further away? This whole discussion about the size of the universe led to the famous great debate before the US National Academy of Science on the 26th of April of 1920. And here are the two models that were discussed as part of this great debate. Shapley, the famous astronomer, argued that the Milky Way, there is only one Milky Way out there. It's only one such large object, and this is essentially our universe. So you have the Milky Way, looking here from the side, it's about 300,000 light years across, 30,000 light years thick, and you have all the spiral nebula that I showed you photos before are simply very close objects that belong to our Milky Way. On the other hand, Hippocrates, he championed the idea that the spiral nebula are in fact island universes, like as big as our own Milky Way, but very, very distant, and therefore you cannot see them in details. So this is the model he proposed. You have the Milky Way here with the star that is our Sun, and it's about 50,000 light years across and about 6,000 light years thick. There is nothing between the Milky Way and the island universes, these other spiral nebula, so it is a long, long distance out to the next island universe. Similar to the discussion about the geocentric and the heliocentric model, here in this discussion, both sides had very good arguments and the case could not be settled. It ended up in a draw. It took another few years to find the answer to which of the two models is correct. It was the famous Edwin Hubble on the 6th of October 1923 who observed with the telescope a very special type of spiral nebula that I show you here on the photographic plate. On that night he took this photo and he identified Nove stars. That's why he put these N letters here and ticked the position where he identified Nove. But then he also realized suddenly that one of the novae was in fact a variable star, a Cepheid star. And that star belonged to this Andromeda nebula. So in other words, if he can measure the distance to this single star, which is part of this nebula, he could also measure indirectly the distance to the galaxy, to this Andromeda galaxy, Andromeda spiral. And that's what he did. Luckily, Cepheids are a very good distance indicator. You can use the periodic behavior of the light curve as a measurement of their distance. And that's what he did. And he wrote a letter to Shapley saying, I believe the range and median magnitude are near 1.0 and 18.5 respectively. And the conclusion out of these measurements was that the Andromeda Nebula is in fact 700,000 light years away from us. So a much, much larger distance than what was predicted for spiral nebula by the model of Shapley. Shapley immediately realized the impact of this measurement, and he wrote Hubble back. He immediately realized the impact of this measurement and of this distant measurements of the Andromeda Nebula, and he wrote back to Hubble, this is the letter that destroyed my universe. So he realized his model was not the correct one, but it was the island universe model that is a better description of our universe. Now let's have a look at some of these beautiful galaxies or spiral nebula as they appear in the sky when you use a telescope like the Hubble Space Telescope. It was realized that there are many, many other Milky Ways out there, billions of light years away from Earth, and they have all this beautiful spiral pattern here, like M51, and here sometimes you see them face on. It looks by just looking through these different images, it becomes clear they're relatively flat in their appearance, round, flat objects where all the stars are arranged and the gas. Sometimes you see them almost edge on, like this in this case or here. Sometimes they are interacting, like as you can see here. So there are millions of galaxies out there similar to our own Milky Way, and each of them have many, many billions of stars. So you're wondering, how does that work together? I mean, we live here in the Milky Way, which we identify as a beautiful strip in the sky of a bright region with many, many stars in it. And then you have the Spiral Nebula, which look totally different when you see images like this. So how does that geometrically work out? I like to compare this with the giant Ferris wheel analogy. When you're standing in front of if you stand in front of a giant Ferris wheel, you realize most of the light that you see from the Ferris wheel is essentially distributed in a disk with slightly a different angle. Very quite comparable to a galaxy which looks like that. Now what happens when you take the ride and you go actually on the Ferris wheel and see the light then? How is the light distributed in that situation? In fact, because you are now in the disk of the Ferris wheel, all the light is now distributed in a 360-degree circle around you. That's exactly what we see here with the Milky Way. Because with our Sun and the Earth, we are living in a galaxy we call Milky Way. Therefore, we see this as a strip in the sky going 360 degrees around us. If you could step outside of our own Milky Way, it probably would look something like this. Our Milky Way is a spiral nebula, and the location here would roughly indicate where we are living with our Sun, in one of the arms of the spiral galaxy. So the Earth with the Sun and the planets are located slightly off the center of the Milky Way. The entire size of the Milky Way is of the order of 100,000 light years. So if you have a friend, if you live here, if you have a friend and you want to communicate over there, it takes 100,000 years to get the message across. And it takes another 100,000 years to receive the answer. A Milky Way, a galaxy, every single galaxy that I showed you before, essentially consists of huge numbers of stars. In the case of the Milky Way, it will be of the order of 300 billion stars. This is making up a galaxy like our own. Now, I show you a little movie here that shows roughly how we imagine today the universe looks like. So we have here indicated with the arrow, that's a simulation, so this is not real, but this is a very close simulation, very close to what the universe is expected to look like. We have a galaxy labeled here as the Milky Way, and we are now flying through the universe, and to show you a couple of features. The universe looks like a little bit like a neural network. It has many, many empty spaces, but then large numbers of small galaxies we call dwarf galaxies, and then bigger galaxies, which are the spiral and the elliptic galaxies. Let's have a look. If you can browse through, here we go. So if you could take a spaceship and fly through space away from our Milky Way, that's how the universe would look like. So you see these filaments, you're coming across beautiful galaxies here, a spiral galaxy here, and then smaller galaxies, and then you have sometimes huge constellations, arrangements, associations of galaxies here, which we call galaxy clusters. So you have thousands of big galaxies right at the same location. This is how we imagine the universe looks like in our models. Now, the question we can ask ourselves, is that it? Can we all go home tonight and satisfied, knowing that we have a good understanding of how the true universe looks like we're living in? You probably guessed it already. The answer is no. There is a dark side to the universe. Since about the 1980s, there is increasing evidence that, observational evidence, that about 80% of all the mass in the universe is made out of dark matter. And this is not dark matter like black holes or neutron stars or planets. It is in fact a very exotic type of hypothetical matter that is invisible and interacts with us, our own world, only gravitationally. Now I show you here a little dark matter simulation of our own Milky Way, how the mass distribution of the dark matter is expected to be around the Milky Way. Let's have a look. So here we have, this is all dark matter, although it's shown here in bright colors. It's actually the dark matter that slowly forms over time. That's a time movie. It shows you how these different dark matter halos accumulate and merge together to form a Milky Way halo. Let's start the movie. So you can see here, initially with the large number of these subhalos that form and merge together to build a bigger halo that forms here right in the center. And over time, which is indicated here with the redshift, we have a system that we think looks very similar to our own Milky Way. And there are two fundamental observations that come out of these supercomputer simulations. Two observations, namely we have the number of objects that we expect, number of subhalos, of dark matter subhalos that we expect around the Milky Way. About 500, if you do head count, between 500 and 1,000 dwarf galaxies, objects that look very small because of this dark matter size are expected around the Milky Way and distributed in a spherical symmetric distribution, as you can see here. Now this high resolution simulation can be now directly compared to what we actually observe around the Milky Way. Let's have a look at what we see there. This is a graph, a figure that shows you the Milky Way satellite census in 2011. So we have the Milky Way here as an edge-on feature, right here the disk of the Milky Way. And you have labeled here in red, the red dots are labeled the dwarf galaxies that are found around the Milky Way. So if all the dark matter that I showed you before, all these dark matter clumps, form enough stars, you should see them as small little dwarf galaxies being distributed around the Milky Way. What is immediately clear from this comparison between the previous slide and this one here is that the numbers are vastly different. Only about 27 dwarf galaxies are known by today. And the distribution doesn't seem to be homogeneous. In fact, they are following essentially this yellow strip here, which is called the disk of satellites, which is an arrangement totally unexpected and not predicted by cosmology models. A fundamental question that we are trying to answer today is, what is the origin of this discrepancy? I mean, there are two possibilities. Is the theory of dark matter incorrect on galaxy scale, or do observers simply overlooked hundreds of these dark matter clumps with their associated dwarf galaxies? These are the two fundamental possibilities to explain the discrepancy between the models and the observations. Now, in order to address this issue and to find a possible answer, we here at Australian National University and the Research School of Astronomy and Astrophysics, we invested $10 million in a new instrument, a new telescope, which is called the Sky-Rabbit telescope, as shown here. The Sky-Rabbit telescope has a huge CCD array, so essentially a huge camera, and this camera covers a very large chunk of sky with one single image. This shows you the footprint of the camera compared to the size of the moon and compared to the large Magellanic Cloud that you see here in the background. With this camera, the Research School of Astronomy and Astrophysics wants to scan the entire southern sky blindly. So we don't look at individual objects, but we actually scan the entire sky, accumulating of the order of about 150 terabytes of data, of imaging data in different photometric bands. With this imaging data, we'll be able to data mine the information out of these images to look for very elusive, optically elusive objects like these dwarf galaxies predicted by cosmology theory. As part of this effort, I'm running the Milky Way Satellite Survey, which is this initiative to search the entire southern sky, which is shown here with all these dots. These are individual pointings. The Scanmapper survey, the Scanmapper telescope produces a survey that scans the entire southern sky blindly. It's a 5-year program, and we analyzed these 150 terabytes of digital images to search, among other things, for these predicted dark matter dominated dwarf galaxies. What we want to address as part of this project are 3 main questions. How are the dwarf galaxies and the dark matter distributed around the Milky Way? So we hope to find many of these dwarf galaxies and the associated dark matter to see how they are distributed in the southern sky. Is the current cosmological model consistent with the most accurate observations that we have at the moment with the Milky Way? Another very important question. Is this discrepancy resolved, or does it still persist after the major survey? And every single object is very precious. Every single dwarf galaxy that we expect to find, we want to physically and chemically analyze to find their properties, and in order to understand what makes them the faintest galaxies that we know in the universe. Now, if that was all a bit overwhelming, talking about galaxies, the size of the universe, planets, other life forms, and the life cycle of stars, I would like to conclude with a quote. All our life we yearn for answers. Why are we here, and where did we come from? How did it all begin? Are we unique in this or is there other life form in the universe? These are all tough questions, but sitting under a dark sky and looking up has somehow brought us closer to the answer. Thanks for listening.